Okay, guys. So next chapter, chapter number 10, which is AC sinusoidal steady state circuits. So let's go ahead and once again, we are studying only the steady state response of these circuits, although there is a transient response, because anytime, as I think discussed last week or on Monday, anytime you have energy storage components, you will always have a transient response, right? Because there's always, it takes some time for energy to store to the maximum value, and then the cycle starts that it starts storing and dissipating energy with a fixed interval, sinusoidal, right? But before the first, the first energy is stored in inductor and capacitor, it takes some time. And we are going to ignore that state. We're going to ignore the transient state and then go to the maybe the third or fourth cycle when it settles down between the two values. That is the peak value on one side and the peak value on the other side. So that's what we are looking at as the steady state response when the input source is a sinusoidal source, or input sources are sinusoidal sources. Now, you guys, all of you have done sinusoidal response, and all of you are familiar with sinusoidal waveform as well. So our sinusoidal waveform, of course, is a sine wave and cosine wave. You can have, mostly we use cosine wave because cosine wave translates into the complex frequency. But I'm just going to draw sine, and we all know that sine wave, let's say this is any signal x of t, can be a voltage signal or current signal. So of course you have the peak value of that x of p, you have the time period of that t, and then frequency, which is f, which is reciprocal of the time period. In the time domain, you write down the equation of x of t as the peak value sine or cosine 2 pi ft plus theta. 2 pi f, of course, is omega, which is angular frequency. F is cyclic frequency. Cyclic frequency is in hertz or cycles per second, which is f, and omega is in radian per second. That is, if you're rotating around an axis, then how many angles, how many radian per second, how many radians you're covering per second, that is given by omega, and how many cycles you're covering in 1 second, that is given by f, which is cycles per second, which is also hertz. And of course, omega is equal to 2 pi f, so f is equal to omega over 2 pi. As I said, everyone should be familiar with this thing. The steady state analysis is not done in the time domain. Why? Because, again, integral differential equation is kind of hard to solve in time domain. Because anytime you have capacitors, anytime you have inductors, and you're solving for integral differential equation, because capacitor and inductor, of course, their voltage and current are related by a differential equation. So we just discussed the second order equation RLC circuit, the first order equation RL and RC circuit. But if you have more capacitor, more inductor, then the equation in time domain just become very complicated to solve. Therefore, when we are discussing the steady state responses specifically, we convert the circuit from time domain to complex frequency domain. So the circuit will be converted from the time domain that is as a function of t to the frequency domain, complex frequency domain, as a function of j omega. And once you do this conversion, then your circuit becomes linear in the complex domain. Linear means you can apply the same rules that you apply for DC circuits. The only difference is going to be now you're dealing with complex numbers, right? So resistance do not change, but your inductance and your capacitance, we convert them into, anyone? Into reactance. And once you convert them into reactance, then the unit of that is ohms. So now you can add all the components either in parallel, series, whatever. You can apply everything that you do in DC domain. The only difference again is going to be you are dealing in the complex plane, so a complex frequency you are using. But once again, if you are using, if you are dealing with equations, right? If you're writing the equations like you did for DC circuit, you don't care if the variable is a complex variable or it's a real variable. It's just a variable, right? And once you analyze the circuit, you put down the equations. Okay, this is you're gonna solve using this method, and everything is in terms of variables. Irrespective, again, variable can be real number, variable can be complex number. Once you have the final equation, boom, you're gonna just put all the values in MATLAB. Now the number in the MATLAB are going to be complex, and MATLAB can of course give you the result as a complex number. So once again, if you start doing the same, and that's where I have seen, especially in the AC circuit analysis, I've seen so many mistakes, because again, students just they struggle crunching the complex number at each step. It's not easy, right? So you can go from polar form to rectangular form and this and that, and it just become, now again, you need to have the understanding of that, remember, and that's what I told you, that make sure you review the complex number. You must have understanding of the manipulation of complex number. How do you multiply them? How do you add them? How do you divide them? How do you go from rectangular coordinates to polar form to rectangular form? Once you have that understanding, then again, you use technology, use MATLAB, use your calculator. Again, if you can do programming in your calculator, by all means, you can use your calculators. I'm just going to use MATLAB because, again, you can create programs easily. You can use those programs easily. So we are going to convert everything from time domain to frequency domain. That is your signal. If your signal is x of t, xp cosine, and it has to be a cosine signal. If it is sine, then add. How are you going to convert sine into cosine? Who's going to tell me? But you add 90 degrees or you subtract 90 degrees? You add 90 degrees. So it's going to be sine omega t sine cosine 90 plus cosine omega t sine 90. So you add 90 degrees, right? To convert sine into, no, sorry. To convert sine into cosine, you're gonna do cosine omega t minus, right? Minus 90. You're going to do a negative 90 here. It's going to be cosine omega t cosine 90. That's going to be 0 plus sine omega t sine 90. Sine 90 is 1. So you're going to subtract 90 degrees. Cosine omega t minus 90 is going to be sine. Okay, but your signal has to be in cosine when you're converting it into the frequency domain. So if your signal is, and again, why it has to be cosine, you can look at the derivation in the book. I don't have time to go over that derivation, but the result of that derivation you will see is, if your signal is in the time domain, then in the frequency domain, you can write this signal as a complex number as a function of j omega as the magnitude and the phase. You suppress the frequency and cosine. Now, that doesn't mean the frequency is suppressed. In practically, the frequency is going to be there, your circuit is running. It's only done to solve the circuit. And if your input signal is given in time domain, once you solve the circuit, you find your currents, you find your voltages, you go back to the time domain when you write the final equation, right? So basically, if let's say this is your result, your final result in the frequency domain, then you're going to go back and represent this result in the time domain by writing xp cosine omega t plus theta. This is not going to change. The only thing that is going to change is the peak value and your phase, right? The current, if you're finding current or voltage here and there, the only two things that are going to change is the peak value of that quantity and the phase of that quantity. Frequency is not going to change, and cosine is going to be part of that. So once you are going from your frequency domain to time domain, you just go opposite. You write down the peak value, cosine omega t, plus the phase that you get. Yeah, go ahead. No, not changing the phase. Phase is still the same as the phase of your signal. You're using that phase. You're not suppressing it. You're using the phase. You're only suppressing cosine omega t just for the sake of the solution, because frequency is not changing. your frequency is still going to be the same for the circuit, right? Phase can change, peak value can change, but frequency is not going to change. If omega changes, your frequency changes. Yes, yeah, right. All right, so any signal, whether it's a voltage signal or current signal, I'm just taking it as a generic signal, xt, in the frequency domain is going to be represented as a complex number. This is the phasor form of xt. And it's going to be represented as the function of j omega, which is xp theta. If you have a resistance, of course, in the time domain and the frequency domain is the same. R in the time domain and R in the frequency domain. So that does not change. If you have inductance, of course, inductance is in the time domain. And what is the reactance of the inductance in frequency domain? XL is what? I'm sorry? J omega L, yeah, J omega L. And again, this is ohms, this is ohms. And if you have a capacitor, of course, in time domain, you have capacitor. And in the frequency domain, XC is what? 1 over j omega c or negative j over omega c. That's in the frequency domain in ohms. So once you convert everything into ohms, then of course you can apply the same rules that you're applying in the real domain, that is in the DC domain. The only difference again is that you have the complex numbers now. How many of you did review the complex numbers before coming to today's lecture? You have not. Anyone who reviewed the complex number? Because again, you're dealing with complex number, you need to know complex number. You can use whatever, but I just want you to review and know when you are using complex number. I don't want you to just close your eyes and then use MATLAB. So even if you're making a mistake, you're gonna blame it on MATLAB. I was like, no, you're making a mistake. MATLAB cannot make a mistake. It's cannot give you whatever you're putting in there. All right, complex plane. Once you have a complex plane, you have real numbers on x-axis, negative real number on negative x-axis, imaginary number on y-axis, and negative imaginary numbers on resistance. Where does the resistance lie on this complex plane? Who's going to tell me? Real part, always real. This can be different values of resistors. R1, R2, R3, whatever. That means if you want to write the resistance in terms of polar form, then you can write that down as the magnitude and angle 0 because it's on the real axis. Angle is 0. Where does the reactive impedance lie on the complex plane? J omega L. So J omega L, let's say here. So that's XL is equal to J omega L. Now J omega L, XL, you can write this down if you want to write down as a complete complex number in rectangular form or Cartesian, 0 plus J omega L. 0 is the real part and omega L is the imaginary part. Now, if you want to convert that into polar form, remember this is the rectangular form of the complex number, A plus JB. When you convert it into polar form, how do you convert that into polar form? If I want to write XL in terms of polar form, what will be the polar form of XL? Magnitude and angle. What is the magnitude of XL? Omega L. Omega L is the magnitude of XL. And what is the phase of XL? 90 degrees. Very good. Because it lies here, J. And what about XC? XC is 0 minus J omega over omega C. What is this in polar form? This is the rectangular form. What is the magnitude? 1 over omega C negative 90 degrees. Very good. Okay. Now, any number, any voltage, any current that is given in one of the four quadrants, if it is given in the rectangular form, you will have to convert that into polar form, because not for the sake of multiplication division, but if you're giving as a final result, remember in the time domain, you need the peak value and you need the phase. Now, if your calculations are usually done in rectangular form, MATLAB cannot do polar form calculation, polar multiplication. So polar numbers always have to be converted into rectangular form, and then MATLAB can manipulate them. But your final result has to be, if you have to display that result, either in the phasor domain or in the time domain, it must be in magnitude and the phase. Remember that, magnitude and the phase. And if you have to do the time domain, then of course it's going to be magnitude cosine omega t plus the phase. So again, that's where you need to understand how to convert the rectangular coordinate into polar form, polar coordinate into rectangular when the number is present in either of these quadrants. So how many of you know how to go from rectangular form into polar form? If a number is given in rectangular form, let's say if your voltage Vj omega is 6 plus J3, and I want to write this down as in the polar form, that is magnitude and phase. Who is going to tell me how I'm going to convert this into, how I'm going to convert this into polar form? Magnitude, what will be the magnitude? How do I calculate magnitude? Say it again. Yeah, 6 plus J3. So how do you calculate the magnitude? What is the formula to calculate the magnitude of a complex number given in the rectangular form? Okay, so a square plus b square. What is a in here and what is b in here? All right, so magnitude is going to be 6 square plus 3 square. And what will be the phase? How do you calculate phase? Tangent inverse of y over x, 3 over 6. Very good. That's going to be the polar form. And again, instead of looking at the computer at this time, make sure you know this beforehand. You don't have to keep looking at the computer. You should know this. Remember that. You should know this. Now, this is easy if the point is in the first quadrant, right? This point is in the first quadrant. Both are positive. What about if the point is in the second quadrant? How do you calculate it? Let's say if your Vj omega is negative 6 plus J3. Then what will be the magnitude? How do you calculate magnitude if the number is negative 6 plus J3 in the second quadrant? Magnitude does not change. Magnitude means what? It's the same thing. That's what I'm asking you, and you should say this. It's going to be the same, a square plus b square, right? The magnitude does not change. It's still going to be negative 6 square plus 3 square, right? A square plus b square, which will be the same as 6 square plus 3 square. Now, how are you going to calculate the phase? What will be the phase? Yes, go ahead. Well, it'll still be tangent, but how are you going to calculate it? Okay, so tangent inverse of what? Tangent inverse of? Okay, so calculate what is tangent inverse of negative 3 over 6 in your calculator. And tell me if that will be the correct angle for this point. Calculate in degrees, if radians or not. Or use MATLAB, whatever. In MATLAB, A10 is tangent inverse. A10D is in degrees. Yes, what angle did you get? Okay, do you think negative 26 is the correct angle if the point is in the second quadrant? what angle you're expecting in the second quadrant? Huh? No, what is the range of the angle in the second quadrant? 92? Between 90 and 180. You're getting negative 26. What is the problem then? It's giving in the fourth quadrant. It's given in the fourth quadrant. So you have to add what? 180 into that, exactly. You knew that, so that's why I didn't ask you. Tangent inverse of whatever, 3 over negative 6 plus 180 degrees. So if your point is in the second quadrant, then you have to be careful that don't just believe what tangent inverse is giving you in your calculator. Make sure you look at where the point is located. Because if you just write down negative 26 degrees, logically it is incorrect. And your result is going to be incorrect, of course. So be very careful as where your point is located. And based on that, decide if your angle is correct or incorrect. And similarly, if you're in the third quadrant, remember magnitude is the same. The equation is not going to change. Let's say you have negative 6 minus j3. So magnitude will still be calculated, negative 6 square plus negative 3 square. So it's still going to be the same. Magnitude, of course, is an absolute value. That doesn't change. What about the angle? How are you going to calculate the angle for that? Go ahead. If you apply tangent inverse, what you're going to get? Yes. 26 degrees, is that the correct angle or not? What do you think? All right, what is missing then? So if you have both negative values, it is giving you angle in which quadrant? It's giving you in the first quadrant, because the calculator or even MATLAB, it does not care about if your y-axis and x-axis both are negative. It cares about negative x over negative y. Negative is positive. So it takes the positive value and gives you the angle in the first quadrant. So now what you have to do in order to get the correct angle? You have to, well, add negative 180 degrees, because if your angles are in the first two quadrants, you go counterclockwise. And if they are in the third and fourth quadrant, you go clockwise. That's how you're supposed to give angles. If in the first, again, if you give in more than 180, that's fine. Yeah, it's still going to be fine. But in general, in engineering or in math, the first two quadrants, you go from 0 to 180. The third and fourth quadrant, you go clockwise, 0 to negative 180. So between, you have to give angle between 0 and 180, whichever is smaller, either the counterclockwise or clockwise. So you add basically negative 180 degrees into what 26 you're getting, and that's going to be your correct angle in the third quadrant. So tangent inverse of negative 3 over negative 6 minus 180 degrees. That's going to be your angle. And the fourth quadrant is basically it's going to give you the correct result. 6 minus j3. Magnitude will still be the same. 6 square plus negative 3 square. And angle, again, if you calculate using tangent inverse, it's going to give you the correct result. It's going to give you the fourth quadrant, negative 3 over 6. And your angle is going to be correct. You don't have to add any positive or negative 180. It's going to be between 0 and negative 90 degrees. What do you mean?
So because of the negative 3 over 6. Flip that negative as a positive 3 over 6.
It's going to be in the first quadrant.
But what if we also then did negative?
It's not going to be negative 90 degrees. So yeah, so let's say this is your angle in the first quadrant. You're looking for this angle in the fourth quadrant right here. If you do negative 90 degrees, so let's say this is 20 degrees, and your angle actually was negative 20 degrees. If you add negative 90 plus 20, it's going to give you negative 70 degrees. So that's going to be incorrect answer. Yeah. So this is just a very brief overview. Again, as I said, you have to do thorough revision of this, and you have to be prepared as not to make any mistake based upon where the point is located, whether the point is given in numerical form 6 minus j3 or it's given in variables. Because sometime when you are converting an in control system or something, or even here in circuit analysis, you will see R over L omega L plus J RC over 2L, something like that. Like you're going to see a function written over here, right? So these are, of course, this is A and this is B, although it will be given in terms of equation. So the same rules apply here, irrespective how complex it looks like. The same rule are going to apply here, right? Magnitude you're going to calculate the same way. A square plus B square is the magnitude. And angle is going to be the same, tangent inverse of B over A. Right? So keep that in mind. And again, it can be either negative, this can be negative, this can be positive. So all those rules will apply here, although the number is going to look like, oh, this is a very dangerous number, it's a very big number or something, but it's not. Big is okay, because again, this is going to be just a single number and this is just going to be a single number. So the same rule is going to apply there as well. Okay, so this is just a very, very brief discussion about that. If you're going from polar form to rectangular form, how do you do that? Right, this was for rectangular to polar. If you're going polar to rectangular, how are you going to convert 5 angle 70 degrees into A plus JB? Or, but you have to put J. Yeah. So opposite is easy. Irrespective in which quadrant it is located, you will still use the same formula. It's going to give you the correct sign. Either this will be negative or this will be negative based upon the angle. So polar to rectangular is straightforward. That's not difficult. Rectangular to polar is where you have to be careful. Okay, some important function in MATLAB that we will be using that are helpful. The first one we use very commonly is absolute function. Absolute basically calculate the magnitude of a complex number. Angle function, which calculates the angle of a complex number. If it is given in rectangular form, then you can calculate using angle. So it takes care of that first, second, third, fourth quadrant. You don't have to add or subtract 180 or positive 180. Angle is going to take care of that. It's going to give you the angle corresponding to the number that you are entering, which is written in the rectangular form. In MATLAB, you cannot write a number in polar form. You have to have the number in the rectangular form. Now, A10, of course, A10 is tangent inverse, but again, if you use this, then you have to be careful about the quadrant in which the point is located, because it's going to do the same thing. If you don't add or subtract positive 180 or negative 180, then it's going to give it may give you the incorrect angle. Now A10 2, and by the way, if you're calculating in degrees, which we do most of the time, then you can use A10D and A10 for degrees. A10 is, you don't have to be careful about the quadrant. But A10 is, it takes y comma x. So you put the value of y. If I remember correctly, you can of course check in MATLAB help. You put the value of y and you put the value of x, and then it gives you the angle. And it's going to give you the correct angle based on the sign of y and x. Of course, A10D, you're going to do y over x. And that, of course, you have to be careful about the quadrant. Then you also have pole to cart, polar to Cartesian. And this is, I think you have used it with me in the software class as well, polar to Cartesian. And likewise, you also have a built-in function, card to pole, which is Cartesian to polar. The only issue with polar to Cartesian is the output is going to be separate x and y. So it's not a single number. And likewise, card to pole is going to give you, of course, your angle and your magnitude as two separate entities, which it should be. But the angle is going to be in radians instead of degrees from this one. And polar to Cartesian is going to give you x comma y as the output. So if you have to create one number, then you're gonna do x plus I, x plus minus whatever, x plus I times y. I, of course, is your imaginary square root of -1. Now, what I advise you, I think you did that in software class. There was one exercise in software class that I asked you to do, in which you enter the polar form, polar number, and then it gives you the rectangular form. Use that exercise, because that exercise is going to come very handy. Was exercise, I don't know, and if you don't have it, then you can always write that, create that exercise. That's not a difficult exercise. It was a function, actually, sorry, not that you created. But anyways, okay, so what we are going to do, we have 10 minutes. We're going to solve at least one circuit, and we'll see how it goes. And once again, I'm not testing your complex number knowledge, but I do expect, as I say, I do expect that you have complex number refreshed. Numerical manipulation of complex numbers, polar Cartesian, Cartesian polar. I expect that everyone should have that knowledge. So in case if you don't have MATLAB or something, you should still be, you're going to take more time. It's going to be time consuming, but at least you will have the knowledge of taking time, but doing it correctly. And that's what I want, that if you don't have technology, at least you know how to do it. Okay, yes. Okay, let me check. So you were creating functions. User-defined functions. So that's user-defined functions. Oh, okay, I notated that. That is exercise 14, I think. Yeah, exercise 14. So in this exercise, you are giving r and theta as your input, and it is converting it into a rectangular form, because again, in MATLAB, you have to use rectangular form. So that's exercise 14 that you created. So keep that exercise with you. It's going to be very helpful. I didn't know I saved it with all my annotation. I usually don't do that. I'll fix it. I have the Word file, so. Okay. All right. So what is the exercise that we're in? This is a simple exercise again. So let's do it quickly. And again, do not worry about that you're using complex number. It's just a variable, remember. Because many of the students are just scared of complex numbers. And rightfully so. If you're using your basic calculator and then simplifying equation at each step with complex number, yeah, the simplification may become a little too heavy. But again, if you're keeping that as a variable, then it's the same as you're doing a DC circuits. VSP is 10 cosine 2000 pi t plus 30 degrees volt. Okay, so this is your circuit. Again, very simple circuit. And again, do not worry about the complex number. It's just 4 components and a source. And what we have to calculate is determine and this is not, many students confuse this with RLC circuit that we did. Remember, if your source is not a DC source, then you're not going to apply the transient analysis of anything. Your source is an AC source, you're going to apply steady state sinusoidal analysis. Okay, so you're going to convert everything into complex frequency domain and then solve the circuit. Once you have IL j omega and VC j omega, then you're going to go back to the time domain and write it down in terms of the time domain equations. Your frequency is not going to change. The only thing that will change is the magnitude of each quantity and the phase of each quantity. So when you are solving for sinusoidal steady state response, the first thing that you do is what? From time domain, go to the frequency domain. Write everything down on the circuit in terms of the frequency domain. So that means I'm going to use another color. I'm not going to redraw the circuit, just use another color. That means this will be Vs j omega 10 angle 30 degrees volt. R1 and R2 are not going to change. L is going to change into XL. And what is XL is going to be? J omega L. Now, what is omega? Who's going to tell me? In this circuit, what is omega? 2000 pi, exactly. So this is omega t, remember. So this is omega 2000 pi. So I'm going to go ahead and put all the values in my MATLAB so I can just, and you do the same thing, guys. Again, I'm doing it. You should do it as well so that you don't spend time when you are doing the solution. You spend time on the analysis, or not on the solution. Okay, so let me put it here so everyone can see. So now your XL is what? XL is I times omega times L. J 125.6637 ohms. And your XC is negative I over omega times C. Oh, negative 1, no, negative I over omega times negative J 159.1549. So X of C is negative J 159.15. Yeah. Because it's going to give you, if it's a complex number in MATLAB, it's going to give you in terms of A plus JB always. So if A is 0, then of course it's going to be 0, because for reactance, it's just an imaginary value. There's no real part associated with the reactance. So it's showing you that the real part is 0 and the imaginary part number is this. Because J omega L and negative J over omega C, there is no real part of that. It's only the imaginary part. If it is an impedance, R plus JL, then it's going to give you the real part as the resistance and the imaginary part as the reactance. Yeah. Mm-hmm. And you will see that because we're going to solve in terms of impedance. Okay. So again, think about the analysis, guys. Don't think about the complex number and solution. Because observe it's just a variable. XL, XC, R1, R2, and VS. Just 5 variables. Now, we are looking for ILJ omega. So we're gonna be looking for instead of ILT, we're gonna be looking for IL j omega, the phasor form, and we're gonna be looking for VC j omega, the phasor form of that. This is what we're looking for. So now, who is going to tell me in this simple circuit? Who is going to tell me? Think DC again. Think DC. Don't think AC. Think DC. How are we going to find IL and how are we going to find VC? Let me, yes, go ahead.
This is in steady state, right?
Yeah, think DC, don't think AC. Think these are just component, everything is resistor. Think everything is resistor because everything is in ohms, right? So assume everything is resistor and this is your DC source. How are you going to find IL? How are you going to find VC? Okay. VS over R1. VS is not even across R1. That's one way to do it. Yes. Yes, go ahead, Suresh. Okay, so we find total impedance. Yeah, don't call resistance, impedance, although assume resistance, but call impedance. Total impedance, okay, and once we have total impedance, then how I'm going to find IL? VS over? So over the total impedance, because remember, IL is the current coming out of the battery source. So once you have the total impedance, then the current coming out of the battery source will simply be VS over the total impedance. That's IL. How are we going to find VC? If you have a plan, then you can implement that plan. How are you going to find VC? Okay, so we can apply current division because we know the total current, and then we can see how much current is going in R1 and how much current is going into C and R2. So we can apply current division to find current going into C and R2. And once we have that current, then how are we going to find VC? Using Ohm's law. Very good. If we have that current going into capacitor, we can apply Ohm's law because again, it's not a capacitor, it's a reactance, it's in ohms. So we can apply Ohm's law, right? So it's a very simple circuit if you again think in terms of DC. And again, Lazaro, you're making the same mistake. You're saying VS over R1. VS is not across R1. You can see that. You can look at the circuit and you can see VS is not across R1. There's an L over here.
Well, so the reason why I said steady state, I thought there was a short there.
No, it's not DC. Once again, it's not DC. It's an AC circuit. AC circuit means that you have a sinusoidal waveform all the time. All the time it's changing, right? Okay, so first we're going to find the impedance. So impedance, I'm going to call it Z. Now, for impedance, who's going to tell me which one is in series, which one is in parallel? Yes, Mike. How I'm going to find impedance quickly? Hold on, Mike is an answer. Yes, Mike. XC in XC and R2 in series, okay? Okay. XL, very good, excellent. So we're going to do that. So first we're going to do R2 and XC. So R2 plus XC. And again, see how easy it's going to be. Now this is in parallel with R1. So I'm going to use my program RP, irrespective if it is real number or imaginary number. The program works for both, right? Comma R1. So that's going to calculate the parallel between the two. And then this is in series with XL. So your total impedance is 68.639 plus J 92.389. Total impedance seen by the source. Vs and then C. Okay, so we have the total impedance, so we can find the current. So IL, this is going to be IL because IL is coming out of the source, going into the inductor. So IL is equal to Vs. Now Vs, I don't think we have defined Vs, so we're going to define Vs first. Now remember, in MATLAB again, you cannot give 10 angle 30 degrees. You have to convert that into rectangular form. Now if you use that program, You can do that if you don't have the program. Simple, use the conversion from polar to rectangular. That is, Vs is equal to 10 times cosine of cosine d for degrees, cosine d of 30 plus I times 10 times sine d of 30. So that's going to be the conversion from polar form to rectangular form. Magnitude times cosine of angle plus I magnitude times sine of the angle. So once you have Vs, now you're going to go ahead and find the current. IL is Vs over Z. So your current is coming out to be this. And here, inductor current. And this inductor current is in phasor form, but it's in rectangular. So we're going to go ahead and convert that into polar form. So we can again use the program, or we can do Cartesian to rectangular, Cartesian to polar. So we can use that, or we can just do absolute of IL. That's going to be the magnitude. Mag of IL is equal to absolute of IL, and angle of IL is equal to angle IL times 180 by pi. 180 by pi because angle formula gave you angle in radians. So I'm going to multiply that by 180, divide by pi to convert into degrees. So 0.0868 or 86.8 angle negative 23.4 milliampere. It's equal to 86.8 angle 23.4 milliampere. Yes. So again, look at the point where it is located. In which quadrant this is located? It's located in the fourth, so it's negative. Oh, you're talking about me. Yeah, I forgot the negative sign. Yeah, no, yeah, it's negative because it's located in the fourth quadrant. So the answer is negative 23 point. So that's your current IL. Observe how easy it is. It's not difficult once you analyze it. So again, don't get confused with the complex numbers. Solution is easy. Analysis is what you have to do. And again, if you have all these programs, again, if you start doing this manually, it's going to take you 10 minutes. But it took me what, 2 seconds to do this because I know how to do it, right? Parallel, everyone know how to do the parallel equivalent. It can become complicated if you just start putting values. They are 1 over XL plus 1 over R1. You know, if you start evaluating that with the values, it's going to take you time. But again, that formula is not changing. So better to have that as a function and then use the function. Okay, so this is we need this into polar form because our final answer has to be in the rectangular coordinates. Okay. All right, so now, our ILT, like, we can write down the final answer actually. Therefore, ILT is 86.8 cosine. What was the 2000 pi, right? 2000 pi t minus 23.4 milliampere. So that is my inductor current. This in degrees, 23.4 degrees. Now we go to the capacitor voltage. So we know this current is going to be divided into R1 and then impedance R2 plus XC. So let's calculate what is the current going through the impedance R2 plus XC. Using current division. Or what we also can do is No, actually current division is okay. I was thinking we find the voltage, but that's fine. We can just do the current division. Using current division, we will finding this current IC. We're gonna find IC, and this current, let's call this current IR1. So we are finding IC. All right, who's going to tell me what will be the equation for the current division for IC? From the circuit, how I'm going to write down, I know IL, so how I'm going to write down the equation for IC in terms of current division. Don't forget your voltage and current division equations, guys. Those are important. Okay, anyone else? What is the current division equation? Yes, you remember? You know, everyone should know. It's opposite of voltage division. Remember that. It's opposite of voltage division. Don't go deep. There. Just write down. So remember, voltage division is what? Let's say V3. V3 is equal to V total times R3 over R equivalent, right? That's voltage division. Current division is opposite. IL is equal to I total times R equivalent over the resistor that you are trying to find the current. It's opposite of the voltage division equation, right? In this case, we're going to take Z equivalent, of course. So current division, and again, these things you should never forget. Current division is total current, which is IL, times the Z equivalent. And I'm going to write down Z equivalent in terms of the equivalent of R1 and R2 plus XC. So equivalent of R1 in parallel with R2 plus XC divided by the impedance through which the current is going, which is R2 plus X. Remember, in current division, you are using parallel. In voltage division, you're using equivalent series. That's a difference, right? But it's still the equivalent comes on top in the current division, and the component through which you're finding the current comes in the bottom. In the voltage division, the component comes on the top across which you're finding voltage, and the equivalent comes in the bottom. The equivalent is different though. In both current division, equivalent is parallel, voltage division, equivalent is series, right? So let's do this. So we find the current. Let's go ahead and do that. So my IC is equal to IL times the parallel combination of, what is the parallel combination of R2 and R1 and R2 plus XC. So R1 and R2 plus XC. That's the parallel combination divided by R2 plus XC. So IC is this. And then I'm going to convert. Right now, I don't have to give final answer of IC, so I'm not going to convert it. I'm going to leave it as in the rectangular form, because my job is to find, or your job is to find, the voltage of capacitor. So how I'm going to find the voltage of capacitor once I know IC? Who's going to tell me? Ohm's law. Okay, and what the equation is going to be? IC. Yes, times XC. IC times XC. Okay, so let's do that. VC is equal to IC times XC. All right, so this, again, I'm just going to copy in. Too lazy to write it down. This, and I'm going to convert now, since VC is one of the results, so I'm going to convert that into the rectangular form. Absolute of VC as the magnitude, and angle of VC times 180 divided by pi. So 6.32 angle negative 66.7. 6.32. 6 point negative 66. Therefore, VCT is 6.32 cosine 2000 pi t minus 66.7 degrees. And these are your